Okay, I think we'll start. This is what, after lunch, this is how it works, but I actually see this as a silver lining, actually. So I'm Mario Montana, with DNAalgo, and I'll be presenting DNAe2c, so ECC implementation for DNA storage, and the title is, as you see, 10x improvement over RS codes. The agenda will be to cover a little bit about DNAalgo. I'll talk about, why DNA storage, error sources, a bit about the DNA channel, some of the standard codecs that are in literature, and then about the codec itself. Before I jump in, first I want to give a shout out to the real developers. Somehow they let me in to a storage developer conference, and the real developers are in Italy. And I'm here as a presenter, and the people like Alessia Morelli is one of the key people. Some of you may know her. She's in the DNA Storage Alliance. The real point about this is that we've developed a platform and a way to create a codec and compare codecs one against the other. It's the kind of the message that we'll get into. And we're borrowing some of that approach that's been used in telecommunications and in storage. How you can, compare the strength of a given code in a given bit error rate environment. There's an emphasis on that sort of comparison in the technique, a bit like what Dave Lansman was talking about this morning. How do you evaluate one approach versus another? That's one of them. The other is around just the concept of system development and system trade-off. Codecs are a piece of the total pipeline, and it cannot be developed in a vacuum. The channels, unlike telecommunication channels and storage channels, the channels in DNA storage are very diverse, very wide-ranging. So when we talk about, and I'll talk about the standard codes like Reed-Solomon, LDPC, those are developed historically with channels that are applied, we'll say, they were developed by mathematicians, but they were applied to channels that had pretty much a range that we understood, like copper, or like NAND flash that they were showing, or disk and tape. The channel sort of distribution is somewhat. So you apply these codes and they almost become standardized, right? But in the DNA storage world, you have such diversity in the channel, the approach to developing a codec is different. And that's what we want to share, is what is the approach to development. So not just the end result, but the approach is the takeaway that I hope you will get from this talk. Okay, about DNAalgo, so the company is focused solely on developing the codec. It's centered in Italy. The people that are part of this are noted. Sabrina, Reno, Alessia, they're the technical people. I'm the chief talking officer, actually, when it says strategy. I think they got me on board because I have an Italian name and I speak English mostly well. My Italian is terrible, but they still hired me anyway. They're located in Italy, and I'm a sort of a floating electron in the US. The company's mission is to develop, apply, I should say, information theory to this problem. Historically, the company, people came from applying information theory to NAND flash. So doing, SSD type error correction codes. And we'll use the term codec here loosely in this context, but ECC codes for NAND flash. And again, what the point about it is how to create a code that is both efficient, fast, doesn't have a lot of overhead, that kind of thing. And that's the mission of the company. Where does the codec fit? I mean, in the whole storage pipeline, a lot of you are familiar with it, and I know that right after me is another codec presenter, so I'll be preaching here a little to the choir on that. But as you know, then you basically go from left to right. Here you're starting with the actual native data. There's the encoding scheme. And then you end up with the ACTG representation. So whatever mapping mechanism people will choose, this is where you end up. The sources of errors that we're trying to correct, of course, occur primarily in synthesis and sequencing. And again, to Dave's presentation this morning, I show a lightning bolt in the storage part, but that's not really where many of the errors occur, as we've well noted by Dave. Most of the errors, such as IDS and erasure, are coming from primarily synthesis and sequencing. But what we operate on, our world, is really this world. We start with this, and it's where we end up with a file. And this file has a bunch of stuff in it. And to say stuff, it's basically analogous to the channel or the noise. We're going to basically characterize the noise as another way to think about it, because this was what we wanted originally, and this is what we're actually getting after all the sources of error that come to pass. And so then the inverse is the decoding, and then bringing back the original data. So we operate in this world here. Likewise, many people. So a lot of you that are in the storage world, and those that are here just learning, many companies are developing their own codec, and there's a good reason for that. It's good because they're intimately aware of their channel, intimately aware of their synthesis technique or their sequencing. So it's a very natural thing that the codecs are developed in-house. So when we look at a standalone company, so what's the value proposition of a company that is on a standalone basis? And the value proposition and the strategy and what we deliver are three things. One is we can take the information from the synthesis or sequencing partner and characterize the channel. So it's the modeling and the noise modeling of that. That's one. We are experts in encoding and decoding IP. So there's a lot of knowledge and mathematical experience in that domain. And that IP is what I'll be talking about. In fact, the title of this, the DNAe2c, is the trademark name that we have for a codec that we developed. And it's think of it not just as the actual implementation, but the process, the approach. Because as I said earlier, there's no one answer for a codec. So you have to have more of a tool set to get there and an approach rather than here's the answer. Right? It's not possible to get there because the channels are so diverse. But we do have a library to start with, and so that's what we'll talk about is a stepwise refinement approach. And then the third is that we've developed a simulator that customers or partners, there's more partners here, could use along with us to get that answer, right? To develop a codec within their framework and within their channel information. So these are the three elements of the company as a standalone company, just doing DNA storage codecs. I think why DNA storage? I mean, this would really only be relevant for people who might be here that are wondering about DNA storage. When Dave mentioned today earlier longevity and the woolly mammoth, of course, I have a woolly mammoth in my presentation. But the three benefits of DNA storage overall, I mean, this is not, this is more of a marketing statement for the application space, is longevity, low power, meaning, the storing of it, which again, this is probably not a good picture since Dave said that it should be dry storage, not in a liquid form. But the idea here is that you don't need a lot of power to maintain it, unlike disks and flash and other forms of storage. And then capacity. There's just a lot of data that you can put in a small space. So those are the benefits. I think we all know, at least the people in the DNA storage world, is how do we get to a place where it's really ready for data centers and the real world, so to speak. So there's a big jump still needed to get to this. I'm not going to get into that, the whole thing. We're focused on the codec, and I'll talk about that. DNA storage, I think it was mentioned in a couple of talks today, is inherently full of errors. Errors result in many different places. What I'm going to be talking about is the insertion, deletion, and substitution errors that we have to correct for, and then erasure. There's the step basically of the PCR process and sequencing that could potentially be a place where you could end up with erasure, where strands aren't properly picked up. That's one thing. So when we look at the problem set of error correction, unlike other error correction for other channels, when you have DNA storage, you have the summation of these IDS plus erasure, and that whole summation is unique. It doesn't, in its totality, it doesn't appear in other applications like telecommunications or traditional storage. Basic ECC, I think this is one slide that I can claim that I actually did work on myself because it's very simple. ECC has the concept. Now I'm taking a step back. Error correction was invented basically in a telecommunications type instance where you'd have a code, or you have your payload, and you would add additional bits to go along with that payload, and those bits would help you in terms of correcting, or at first identifying if there's an error. So a very simple code could be a checksum. So then the receiver applies the mathematical calculation and says, hey, there's an error in this frame that came. So you have a frame which is made up of the payload plus error correction, and in other applications you could have headers and footers and tail, all that stuff. But in a very simple sense, you have a payload and then error correction bits. That's a frame. The main purpose of all this, of course, is to improve the likelihood of having the information either transmitted or recovered in the case of a storage application. Now, codes, there is a cost and a benefit. So this is very simple slide that's saying, okay, here this is more of this is not cost, this is the benefit in terms of monetary benefit. And this notion of code rate. If you have a code that's a lot of bits, a lot of correction bits, well, that is going to result in a situation of cost. And it's more desirable to have a high code rate, which is where you have very few bits for error correction and as a percentage of the frame size. So it represents essentially less overhead. A code rate that is lower means that you're using a lot more error correction bits relative to the size of the frame. So the whole point about this is saying that there's an efficiency aspect to error correction codes, and we're mindful of that in the case of this application. I want to step back and the other theme that we wanted to convey in this, besides how do you evaluate one code versus another, we want to get the point across that there are examples of where you had very difficult channels, and through the use of ECC, we were able to solve a problem that was an unintended reality. So let me talk about phone lines. They were installed in, I think, the 20s and 30s when phones were invented, and the medium in that case were simple copper. And those copper lines were designed for 4 kilohertz voice. And along came the internet, and slowly, a lot of us, some of us might remember, there's probably younger people didn't have the traditional dial-up modems, and then, even, and all of that sort of thing. Well, how did we do that? And even today, right? I mean, you can get an AT&T modem, you could get up to 50 megabits, and it's still going through traditional wire. How does that happen? And through the use of ECC and, I must say, DSP technology, which is more about signal conditioning, but the two together get you to a place where you can, with a crappy medium, a terrible medium, you can achieve good results. And so ECC had a benefit there. And as a system design, we wouldn't have done that without a strong, or would not have been able to achieve that without a strong ECC. Another example, as was mentioned earlier, is in SSDs. The medium there, which is NAND, started out with simple single level control and then has moved into MLC and TLC. The point here is that the medium in flash is inherently error prone. It's not a good medium. And in fact, if we think about retention, as Dave was talking about earlier, it's a terrible medium for retention. Bits get written in there, and then who knows if it came back as a 0 or a 1, or in many cases, now that we have 3-level NAND, it's even more difficult to distinguish. And so you have error regions. And inherently, the point about this is that NAND and SSD is full of errors. And without error correction in that sense, we wouldn't be able to have 10 to the minus 14 kind of error rates or frame error rates without error correction. It just wouldn't be possible. So we think that if we now look ahead to DNA storage, the mission we have, or we believe for ECC, is that, first of all, DNA wasn't created for storage use. DNA was created for life. It's a different biological, medium. And it inherently, when we're going through the process of synthesis and sequencing, we generate many errors. The people who do synthesis, and some of you are in the room, and people sequencing, spend a lot of time and energy and research to improve those processes and reduce the errors. But sometimes those trade-offs result in higher cost or time. And what we're thinking about here is that if you could do like was done in telecommunications and in SSDs, if you could bring a strong or highly tuned and flexible codec into the mix and develop it in a way in a way that you're cognizant of the total system trade-offs. So for example, if you could perhaps create a synthesis process that was faster, potentially more error prone, but the codec that could basically correct for, and you could optimize that, then maybe the system trade-offs were worth it. So you could spend less time, less money on synthesis. And I think for those that are in the synthesis world, I'm probably, again, preaching to the choir, but I think if you were able to have a total system approach to it, you may be able to get to a cost point and time point with a strong codec or an optimized one, much like what's been done in NAND and in telecommunications. Enterprise grade storage, of course, as we know, is somewhere around 10 to the minus 14 when we talk about frame error rates. Okay, so that's at a high level, what we're talking about is ECC, basically to summarize that, ECC could make a strong difference in a total solution for DNA storage. One that's economical and viable at the same time. So we'll talk about the errors, the sources of errors, IDS and erasures. I would say most of the IDS errors, as far as we know, are coming from synthesis. We may have some that come from the actual storage time, but very few, as Dave was mentioning. And then also in sequencing, the When PCR is applied, there's a case for saying that it's possible that we may not pick up a strand, and so that's where we may have erasure. The world that we deal in, as I said earlier, is kind of characterized here in what we get basically as an input to our system is characterized somewhat on this column here. Errors are coming from, as I said earlier, from the synthesis process. So you'd have some that are the nature of insertion, some would be substitution, deletion, and then potentially erasure, which would be from the sequencing process. So we would get this file, and the error rates here could be on the order of 1 even to 5%. Sorry. And with that, even with, let's say, the post-processing that one might do with clustering, averaging, trace reconstruction, even after all that, you may end up with you're in a place of even 1 to 2 or 3% error rate kind of built into it. This is what we get. This is what we have to handle in our system. Now, codecs have, as I said, historically been developed in the mathematical applications for transmission and storage. There are a set of them that are pretty well known. Reed-Solomon, LDPC. LDPC is used a lot in SSDs. Fountain and Hedges codes have been applied more recently into DNA storage, and they do well. They can handle cases such as erasure and substitution. Now, when we look at comparing the codes, there's a what they do comparison here in this table, and then I'm going to talk about how well they do, and that's a different comparison. That's looking at the frame error rates versus bit error rate. But in terms of what they're good at, this table is attempting to summarize it. Now, if you had no codec, what does that mean? It means that you're relying primarily on trace reconstruction. Someone mentioned earlier averaging, clustering, and if you're just doing that, you can partially correct for things. And in an experimental world, in a sort of prototyping instance or situation, that would be fine. But if we're talking about enterprise-grade storage, you clearly need a codec. And then when we look at the different standard codecs that are out there in ECCs, like that are listed here, they all have strengths and weaknesses. What we're asserting is that we have an approach here, and I use the word approach because it's not just one basic codec that's tuned and complete. It's an overall approach, especially for dealing with erasure, because that case is a more difficult one to handle with just one answer for a codec. Now let's talk about how you evaluate codecs. This is where I'm switching now into the, how well is a codec function versus in terms of its performance versus what are the things that it can really do, and that was on the previous table. In the standard codec world and ECC world for transmission and in general storage, there's this notion of characterizing the frame error rate versus bit error rate. So if we're saying here we want a target, in this example, of 10 to the minus 12 frame error rate, we would plot how well this particular system is. This is basically a system with a certain ECC. We plot how well does it do as you sweep the bit error rate from low to high. So clearly, at this point, this is not a usable system when you get up here. So the bit error rate needs to be at a certain place in order for this particular ECC to achieve 10 to the minus 12. If you're applying a different ECC on this set of curve, or on this curve, this is saying that this particular ECC algorithm can handle a higher bit error rate and still achieve 10 to the minus 12. So clearly this one, this particular ECC is better than that. And this approach is what we're going to talk about and basically switch gears into, instead of bit error rate, we're going to be talking about deletion error rate, substitution error rate, and sweeping sweeping those parameters from good to bad, and looking at what happens to the frame error rate in that instance. So this particular approach is what we're doing to compare one codec versus another. So if you can imagine in the DNA storage world now, there's a whole set of data in order to do this, and I'll talk about that in a minute. But this is the fundamental concept of sweeping bit error rate and looking at what happens to your frame error rate with a given ECC. Now, when you move into the DNA storage world, we have to talk about, well, what is a frame? Earlier, I showed a very simplistic view of a frame, which had the payload and ECC bits. It's in the digital world. But in DNA storage, we're in the basically a DNA domain with ACTG concepts. And so when we think about frames, in this case, and if we just happen to use a simple mapping here, which everyone would probably say, no, that's not how you would do it. But if you had a simple mapping, this particular set of zeros and ones would be representing this particular strand. And if you have a set of strands now, one can now pick up the concept of, well, how do you develop a frame? So if you had a set of DNA strands and they have, if you recall that other picture I showed, which had all the errors, say, okay, well, how am I going to define a frame? And there's different approaches to it. You could have a very simple horizontal approach. You could have some that sort of spread across different strands. So this is a very simple view. This is basically one strand at a time. But you could have a frame that spans strands, or you could have another frame approach, which says, I'm going to span vertically a bunch of strands and create a frame in a vertical sense. And in fact, this is a better approach to do because it's one way to handle erasures. Because if a whole strand disappears, if you're using this approach and a whole strand disappears, you're dead. But if you do it this way, you might be able to pick up a case, or you will be able to pick up a case where you've lost an entire strand. So this is just saying, okay, in the DNA storage world, you have to define a frame. And there's different ways of doing it. And now that you've defined a frame, you say, okay, I want to sweep, generate with whatever the noise channel is and whatever the data set is I'm working with. I'm going to create a set of, for a given codec, a set of curves which plot the frame error rate versus, let's say, substitution error rate, or versus insertion or deletion error rates. And so you can generate a set of graphs now, all right, and say, okay, how good was that codec as I swept the case? And this is not, I mean, this is where the simulator comes in, and the tool for doing that. There's a lot of, just basically a lot of simulations in order to get there. You can also do this, and you should, with respect to dropout or erasures. So erasures are particularly bad, very difficult, and here it's the same thing, although you could, I mean, not necessarily, you you could say, all right, I've got a particular codec here on the pink line, and I'm going to pick a dropout rate. I'm going to say, well, if my erasure rate is, say, 1%, what frame error rate will I achieve with a given codec at this erasure rate? And clearly, this particular codec here does better at a given erasure rate, right? So this is somewhat of an inverted way of looking at it. The other one, I fixed the frame error rate and swept at, let's say, substitution error rate. Here, we're saying we're going to pick an erasure rate and look at what frame error rate results with a given codec. It seems better in the case of erasure to work on this approach, but you don't have to. It's just this is really more for illustration purpose. So I've talked about the ways in which you can evaluate, and we're borrowing from the telecommunications and storage world. It's sweeping the fundamental, instead of bit error rates, we're sweeping now the IDS error rates, or we're sweeping the erasure rates. And we want to be able to judge how well a given codec implementation works as you do those sweeps in the concept of a frame. And here the frame, as I said earlier, could be defined by you as a user in different ways. Now, the codec that we've developed as a sort of our standard one, which we call DNAe2c, the goal of this codec was basically threefold. We wanted one that you could basically tune it, and I think I heard some other people say about tuning. So codecs are tuned based on the channel, based on the sequencing and the synthesis channels that are there. So we wanted to have a codec that is tunable. The second point is that we want to be able to run many simulations. So we need to create a simulation environment that can just run billions of cycles in order for us to sweep and develop an understanding of the performance of any codec that we develop. And the last is, we want to keep the code rate as high as possible, which is the point I mentioned way back earlier about being efficient, not a lot of overhead. And we want to be able to be highly executable in the sense of this isn't just going to run on, Amazon's, take up 40 servers on Amazon to get an answer. We want this to be something that can be implemented in a server and actually run in real time. And so that's the third goal of this, is that we want to make it that it can actually be deployed. It's deployable, we'll call it that way, in a data center environment, which means putting it in hardware. So I won't get into the actual way that we came up with the acronym, but the E2c, of course, we know is just in general, but we have error and erasures, and that's a key part here, is that this codec and approach is really meant to be able to handle both the standard IDS and erasure problems that you're going to have in DNA storage. So it's iterative in the sense that we can converge using our simulator. It's flexible. And the third bullet here is important. This is where I'm going to get into the point about recovery mechanisms. So we're kind of stealing a little bit of what's used in the storage world. They have error recovery mechanisms. So when things like RAID and stuff, and dealing with real bad things that happen, and how do you solve for that? The analogy here is that erasures are really bad. So how can we develop what we call an erasure recovery mechanism, and correct for those events? And it's not just a standard mathematical answer for that. We call it a trick. And then the last point here is that it's hardware implementable. Oops, sorry about that. I just went to the end. I didn't mean to do that. Let me back up. There we go. So That's when you hit the end button. So let's look at the process. So we start out here with the experimental data. This is basically the data we get from a partner, massive file. And we put that into our simulator, and we develop, actually before we get there, we develop the noise model that goes into the simulator. And we use the simulator to, as I said, generate the different, with a given codec, and or given set of parameters in our codec. And we say, all right, did we hit the frame error rate? No. We go back and we start tuning the parameters. And we keep doing this in an iterative style. And then we end up in a place where we say, okay, we've got our codec with the proper tuning parameters for this channel. Then we say, okay, that's not good enough. We need to have recovery mechanisms that handle the erasure problem. And what we're showing here is we say, well, if you get a high number of erasures, there's at some point this particular codec that we've tuned and using our standardized codec that's tuned, as the erasure rates go up, we have to kick something else in. And that's what we call an erasure recovery mechanism. And we have different sets of those. So here's implying that we'd have a second erasure recovery mechanism, and a third in the case where you have a high error rate, IDS error rate, and you have erasure errors. So what we're talking about as a platform and an approach is that you have the ability to couple a standard codec, which I say standard, our DNAe2c, couple it with erasure recovery mechanisms, and be able to handle the cases of a high degree of erasures as well as a high degree of IDS errors. That's the approach. The implementation, as I said earlier, is to put this in hardware. And here's an example. This is actually the card that we use, an FPGA from Xilinx, which is very much a standard enterprise data center class card. And we're able in this, with this card and the software we've written, basically to take up to 20 terabytes of an archive size, which in terms, with an assumption of 120 nucleotides per strand, in one day we could process and correct 20 terabytes worth of data in one day with this card. In an hour, that's the same as 800 gigabytes of user data. So we believe that this approach is the kind of approach in the future we'll need. And it, like I said, we're able to implement it, run it. This card is a 10-watt card. I know people have asked in the past what kind of power consumption is needed. This is a standard 10-watt card. Now, to fill in all the answers here, this is to implement just the ECC. If you're going to do trace reconstruction and clustering, that's another card for that. So there's sort of two stages for the complete codec function. Okay, so in terms of comparing ECCs and codecs, we've got, with our simulator, we're able to sweep and evaluate the frame error rates versus the substitution error rates, insertion error rates, and deletion and dropout rates. And we've taken that approach and generated graphs. And in particular, we have, and this is an example, and this is really the sort of technical punchline here, is we have an error set here. This is what we simulated. It's a specific set of data that would have a substitution error rate of 0.01. We fixed that. And we're going to plot the frame error rate versus deletion and insertion error rate. And it's for a given strand length and a given PCR rate. And what we're showing here is that this curve here is the Reed-Solomon implementation. And this is saying that in order to get to roughly a 10 to the minus 8 or 10 to the minus 9 frame error rate, the deletion and error rate needs to be around 0.002, the intrinsic error rate, which is quite low. Reality is that in the real world, it's going to be much higher. This particular curve is an LDPC implementation. So think of these as sort of off-the-shelf standard codec implementations. What we're plotting here is the DNAe2c curve. And here we're showing that we can get the sort of same 10 to the minus 8, 10 to the minus 9 error rate, frame error rate, in the presence of a deletion error rate of 0.027. So this is really what we're saying about a 10x improvement for a given set of data that we've worked with. So in time, what we have a platform to do is to develop more of the characterization and applying different data sets and seeing how the system can perform with that. So to conclude, back at the very beginning of the talk, I was saying that error codes have been applied to examples or cases, I should say, where the media is pretty bad. And I think we'd all agree that DNA storage, DNA is good once it's stored. It handles well, but it's the getting it into the DNA form and getting it out is where the errors occur, not when it's in actual storage. So I don't want to say DNA is a bad medium. It's actually a good medium. It's everything that happens before and after that's bad. And it's a much different channel, as I said, compared to the storage and telecommunication world. We need a way to compare codecs. And I think we've established a platform to be able to do that in a way that's clear and methodical. We've got a case or a set of solutions that we think can handle both IDS and erasure. And it's been implemented in a hardware format that we think could then scale into a real data center environment. And we've got, as I said, as a standalone company, we're looking for partners and people that can handle or be interested in using this platform and developing a codec that works for their process. Excuse me for the scratchy voice. I'm pretty sure it's not COVID. I don't have that. But anyways, thank you for your time. Yes?
My question was, I was pretty impressed when you said 10x speed up over Reed-Solomon. So I'm wondering, in your proprietary codec, where does that acceleration actually come from? Have you done anything algorithmically, which is a significant improvement over Reed-Solomon, or does this speed up come mainly from the way how you arrange data?
Okay, so let me clarify. The question I'll repeat is, are we faster? Did we implement something that's 10x faster as a speed up? This is not really a speed up. It's a 10x improvement in error performance. So it says that if you look at this chart, right here, here, at a given frame error rate of 10 to the minus 8, if you go down this way, this is the 0.002 roughly. That means, that's saying that in order to achieve a frame error rate of 10 to the minus 8, you have to have a deletion error rate of 0.002 in your native file. If you go, as soon as you go to the right, on this, with this particular codec, the frame error rate jumps, and it's pretty much unusable. If you go over to this line here, this says for the same frame error rate of 10 to the minus 8, we can get there even when the deletion error rate is 0.027. So that's the 10x. So it's the 0.002. So that means we can, the noisiness of the channel, the error rate can be 10 times worse. And we still get, something at 10 to the minus 9. It's still not data center, but it's getting closer. Does that make sense? It's more performance, not a, yeah. And it's achieved, thank you. And it's achieved algorithmically. It's not achieved because it's running faster. It's achieved through the algorithm.
Right, that was my main question.
Yeah, sorry, I didn't get that. So the Reed-Solomon, that's a time. Is that time? Yeah, okay.
Well, you're officially out. Yeah, we have a 10-minute break.
Yes, Daniel.
So what was the cost of running the PGA card for 24 hours?
Well, if you're 10 watts, so if you ran a light bulb for 24 hours, you do the math in terms of kilowatt hours, right? So 10 watts running 24 hours, it's not a lot, right? In terms of, I don't have my PG&E kilowatt hour converter, but 10 watt for 24 is pretty low.
10 watts per hour?
It's 10 watts. That's a good question. Is it when you look at a card, when you run it, it's an instantaneous 10 watts, right? So when you turn it on, it's burning, it's consuming a certain amount of current at a voltage, and that gives you the instantaneous power. If you run that now for 24 hours, then you get the concept of kilowatt hour. And then you look at how many, what do they charge for a kilowatt hour, right? So 10 watts, I don't know, I just think of it as a really low voltage light bulb, which, you run that, it's pretty low. You're thinking about electricity costs, right? Yeah. I can answer that separately. I'll give you an answer to it, but it should be in the pennies, dollars.
A good number to track the cost per terabyte to decode and encrypt.
With the data, with the numbers that I've thrown out here, I could get you that answer. I could do the math. If I did it in real time, I definitely would have a wrong answer. So, but that's a good point. Generally the problem is computational cost. And that's why we wanted to put this in a card so that this is something that could be cost effective. Any other questions? Sorry, I went over time. No? Okay, well, you can catch me later. Okay, thank you.